I'm not gonna lie, we're breaking a lot of rules today, so I'm just gonna dive right in. I have a video or two to play for you here, so hoping they load quick. So give a listen, write down anything you find interesting.
All right, so here's what's happening. There's a gas inside this tank. It's called sulfur hexafluoride. It's a super heavy gas. Sulfur hexafluoride. It's boring. It's inert.
Anybody asked
It's,
what happened
it's
to it.
odorless.
Yeah.
Okay, so it's normally boring, but here, watch this. I'm going to slowly pull the lid off.
Okay.
So that should be perfect. Gary, would you take that little end off over there as well? You see that? Yeah.
Yes,
All right,
indeed.
so let's see if. Oh, it feels pretty good. So let's see if we can float the boat. Okay. Ready? So here we go. Let's see if we can float the boat. Stay there, little guy. Tell me that's not fucking awesome. Isn't that amazing?
Cool.
And
That
this
is
as close to
awesome.
magic as you
Yeah.
can.
Oh my
So
gosh.
is that, no, it's okay. Push it around. It's
That's
okay. So this
crazy.
heavy gas is about 6 times heavier than the air that we breathe. And so I just have it coming through a tube here. And so I'm going to give us just a little bit more so you can kind of see what's going on. Here's what they
Okay.
use it for. Electrical engineers will flood a room or part of a semiconductor or something with this material because it doesn't allow electricity to, it doesn't conduct electricity. So here's a taser.
Yeah.
So all right, so look, so here's the taser. So when I put the taser down inside, here, watch this. When I put it down inside, it stops.
Oh, it stops working.
And now when I bring it back out again, so they will keep it. So if you don't want something for arcing from one place to
Doesn't
another,
conduct
but the coolest
electricity.
thing is this:
Right.
because it's inert, you can breathe it, and you might see something different. Ready? So
Can
come
I
here.
go first?
So
Yeah.
just stick your head way down inside and breathe in. Breathe in. Ready? Now talk to the nice people.
So I'm gonna stop.
Hey,
it
come here, get in there.
Awesome.
All right, so
For some reason, their mics got really low the second they breathed in this gas. So I found a different video where you can actually hear what it sounds like a lot clearer.
I promise to show you something really cool as long as you promise not to try it at home, okay?
No.
Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
The simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
Sulfur hexafluoride, which is 6 times denser than air. I inhale some of that.
And my voice gets really low, although somehow I'm still funny. It's scientific!
So there you go. And if you want, you can find tons of videos. You can see everyone, they're breathing both helium and this compound, sulfur hexafluoride. And that's what I really wanted to focus on today. Oh, boy. Okay. I guess maybe it might not be super intuitive at first why it's like making me pause. I did want to touch on covalent naming just to make sure you've had some experience with it. It's actually a lot easier than all of the ionic naming rules because you just name what's there, and this is the time when you use prefixes. Mono, di, tri, tetra, penta, hexa, hepta. And the idea is you just, you say what's there, with the exception of if the first element, there's only one of them, you don't need to say the mono. So for example, something like carbon dioxide, well, that's 1 carbon and 2 oxygens. Done. Nice and easy. Nitrogen triiodide would be Ni3. Done. Dinitrogen pentoxide, N2O5. So it's like super simple to like make that all down there. But that means if we double back to what the video was about, this compound sulfur hexafluoride, that means SF6. And if I were to try and draw what that looks like, I think I'd have a hard time because the only way I can imagine bonding everything together, I know each fluorine has 7 valence electrons, so can only make 1 bond. Does that mean that all 6 of them need to be bonded to the sulfur? I mean, like, totally not cool because we know that, the limit's 4, right? 8 electrons, that's nice and stable. And that's the problem. So today we're going to go really, like I said, off the deep end. There's a couple things that come together that really help to explain how and why you can get up to 6 or 7 bonds around a central atom. But to really explain that, we have some other phenomena we have to also tackle. I kind of did some hand waving earlier where we learned that, you draw carbon like this, which is related back to the idea that there's 2s2, 2p2 electron configuration. The first two electrons are paired. But then I said bonding carbon, whatever that meant, and you were allowed to draw it like this to allow you to make 4 bonds. Well, why is that? Add on to that the fact that when something like methane gets made, which is CH4, all 4 of those bonds are equivalent. Same energy, same length. So that doesn't really agree at all with this model where you've got 2 electrons in an s orbital and then single electrons in a p orbital. How do you get 4 more electrons into that compound where it's sharing between carbons and individual hydrogen atoms? So the way this all gets worked out is that to make bonds, particularly to make many bonds, there's this process called hybridization where orbitals can blend. The big deal is that to make 4 bonds of the same energy, you need 4 electrons in 4 orbitals that are at the same energy, or degenerate, which is a word we've seen before. But you don't have 4 degenerate orbitals in a carbon atom unless you're allowed to mush around these clouds and mix them up. And so this process happens where S's and P's blend together, and this allows all 4 of the orbitals that you make, because if 4 orbitals go in, 4 orbitals have to come out, are at the same energy, and then this allows this unpairing to happen. Now you can't just unpair, right? It wouldn't make sense to take this electron and just pop it up and leave it there, because that would do the job, but that still wouldn't solve the issue of equal energy. What happens is when the orbitals mix, the energy of the orbitals also mixes, and so when they're degenerate, they're actually 4 electrons at a lower energy than the p electrons would be at, right? So to sum things up, electrons' orbitals will blend in order to make degenerate orbitals to allow unpairing to happen. All in all, this process does decrease energy slightly. You get 3 electrons going down and only 1 going up, so that kind of makes it worthwhile from that energy standpoint. And then these hybridized orbitals are labeled based on what went into them, which I'll show you some examples in the next slide. It is possible to get different kinds of hybridization where you have different mixing going on. So in this case, we're mixing 1s and 2p's. In this case, we're only mixing 1s and 1p. And like I said, we'll see examples of how and why that happens. But hybridization allows you to do this process. And so it's really a question this hybridization, it's not a question of how does it or why does it happen. It's more that we know that this happens, and hybridization is our explanation for what we see. If we see that all this has to be degenerate, this is how we make sense of it. It's relatively simple, now that I just explained all of that, to label the hybridization of the central atom in a compound by looking at its Lewis structure. So what we're going to do is I'm really quickly going to draw in all of these Lewis structures to make my discussion a little easier. And I think these are all structures we've seen before. For this one, I'm going to do this. But it really, it relies on doubling back to say what went into it will be determined by what we're drawing here. So it comes down to using this term called bonding domains. And a bonding domain is a group of electrons that is considered separately from the rest of the electrons in your atom. A bonded atom is an electron domain. Whether it's a single or a double or a triple bond, it counts as 1, and then lone pairs count as 1. And so the idea here is for water, we count up how many bonding domains we have around our oxygen. There are 4. So what orbitals are needed to make 4 bonding domains? Well, if you're talking about oxygen, right, there's 2s, 2p, 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 and that's it, right? There's no more d orbitals in for oxygen. So what gets used is all of those. We would call this sp3 hybridized, and that's the terminology, sp3. For carbon dioxide, we're again looking at the central atom. We have 1 bonding domain and 2 bonding domains, so 2. So what do you need? Well, you need an S and a P, and then you can leave these guys alone. So this hybridization is labeled as sp hybridized. For For this third one, again, we have 2 bonding domains, so that would be labeled as sp hybridized. And for this one, we have 4 bonding domains, and we would label that as sp3 hybridized. So again, you're just kind of counting, right? 1s, 3 p's, 4 orbitals, that's your hybridization. In the case of sp hybridization, you'll see that the carbons have some double and triple bonds going on. You might wonder where those other p orbitals go. The 2 that didn't get used, well, they go into the double bond or the triple bond. It turns out that double and triple bond, those extra bonds, 2 and 3, do not participate in hybridization, which is why a double bond counts as 1. For this bottom one here, which, by the way, I completely did not do correctly. I didn't want to do that. I wanted to do not C3H4, I wanted to do C3H6. So that actually makes sense. So you can actually, in absence of a central atom, you can go atom by atom down your molecule. This one would have 3 bonding domains and would be sp2 hybridized. This one would also be sp2 hybridized, and then this one would be sp3 hybridized. So you can start to think about how the individual atoms look in the molecule and what shapes they take. Speaking of shapes, we're going to get into this a little bit more in a future video, but oh, sorry, I forgot that picture was there. Let me clean this up. You'll notice that I've labeled sp2 and then sp and sp3 in several locations. So you'll notice that there are several ways to get to sp3 hybridized. We have 2 lone pairs and 2 bonds, 3 bonds and 1 lone pair, a single and a triple bond, a double and a double bond. So you'll see here a little picture on the bottom that says there's several ways to get to that sp3, whether it's 4 bonded atoms or 2 and 2 or 1 and 3. Like I said, what do these look like? Well, here's some pictures to kind of help out with that. If you want to pause and look at these before you listen to me talk, totally fine. But the example of sp3 hybridization is on your bottom left of your screen, and it is the idea that you take these orbitals in the x, y, and z direction and the s orbital, and you blend them. And when you blend them, there is some orbital geometry and some weird vector math that goes on. And what you get is 4 orbitals in 4 different directions. You'll see that there's a major lobe and a minor lobe for each of these sp3 hybrid orbitals in comparison to the p's, which are even on both sides. What you then do is you take these 4 hybrid orbitals and you superimpose them. The midpoint where the 2 lobes meet, that's supposed to be your nucleus for carbon. So when you add the 4 of these up, you kind of get one that looks like this, and then you get one that looks like this, and then you get one that looks like this, and then you get one that looks like this, and they all add up to make this shape. And that's the shape that you see right over here. Only the major lobes have been shown. So when you overlap them into one atom, you get that structure. If you have sp2 hybridized, you're not using one of the p's, so that third dimension vanishes, which is why you get this planar structure where everything is flat. There's one p orbital that did not participate. And then for the linear, you're getting rid of 2 of your p orbitals, which is why it's in a straight line in one direction. If this all seems kind of weird, it's okay. I'm just trying to give you a little bit of experience with it. The end goal is that we're able to draw structures and determine hybridization from the structures that we draw. We're not worrying about geometries at this point. So, SF6, if we have to bond all 7 of these atoms together, I kind of think we have to break one of our big rules of bonding. I had said before that you really shouldn't unpair any electrons once they're paired up. But I don't really see another way to get 6 fluorine atoms around this sulfur unless we do just that. So let me finish drawing in the rest of my fluorines here. I think we have to do that, yeah. So we're going to make a single bond here between these 2. We're going to make a single bond here, but the only other way we can connect any more fluorines to the center is if we start splitting these up. Now, if we start adding everything that we just said, let me clean up this structure. How does this happen? Right? How do you make 4 bonds? Well, we said that if you're making, 6 bonds. If you made 4 bonds, you have S, P, P, P. There's only 3 p orbitals. So in the case of sulfur, if we're making more bonds and we have to mix more orbitals to make these bonding orbitals, we have to use a D. Not just one D, we have to use two. That's the only way this works, right? So in terms of our blending, you know, you had your S, you had your P, but since this is sulfur and its valence electrons are in the third energy level, technically 3D is sitting up there. So we could use it. We could use this one and these and these. So our hybridization for this would be sp3d2. That seems to work. And if you wanted to count up your electrons, you can. And this structure is actually formal charge compliant. All the formal charges of all the atoms shown are 0. So it works. And I do want to make a big point of this. Expanded octets, this idea of making more than 4 bonds to a central atom, really hinges upon having access to a d orbital in the actual energy level that you're looking to mix. You'll notice that they're all starting with 3, right? So like you could just say, well, carbon, can't it just do like 2s, 2p, and then look at 3s? One of the rules of hybridization is that we don't see that, it does not happen, and you can only hybridize within your principal energy level. So starting with period 3 and down, sulfur does this, oxygen does not. So other things that I'm noticing here, like where does it end, right? So you can actually talk about other structures. Let me draw these two here. I'll draw BH3 up here. BH3, nice simple molecule. There is nothing up here because boron only has 3 valence electrons. So when this bonding happens, it actually has an empty p orbital going on, unused in bonding. So here we'd have sp2 hybridization. For PCl5, it looks much like SF6, except we have 5 things on our central atom instead of 6. So you might sit there and say, like, well, can't we just add a 6th thing? And the short answer is kinda, but you probably don't want to just keep jamming stuff into these molecules. There's a couple things that come into play. One thing is something called sterics, where everything literally has to fit. And PCl6- probably exists, but like I said, more on that maybe later. Usually I'm going to say where this ends is that you can make as many bonds, provided that you're in the 3rd period or lower, as you have valence electrons. So sulfur has 6 valence electrons, it can make 6 bonds. If you wanted to put 7 bonds on there, usually that's going to incur a formal charge of a negative on that central atom, and that makes an instability where the particle might fall apart. So PCl5, well, it makes 5 bonds because we know phosphorus has 5 valence electrons, so we use all 5 of those. Can you make a 6th one? Probably not. And I keep saying probably, I know, I'm sorry. So just to sum things up, using that idea of maybe if we've got these big, chunky, 3rd period and below elements that can make more than 4 bonds, you are allowed to start breaking up some pairs. Try and draw these structures as best you can. Hit the pause button and do it yourself, otherwise I'll start drawing. For IF3, it's one of these things where like you do it when you have to, but not for no reason. So I think that first bond can still be made into the, unpaired electron, but then we're going to have to break up one of these. So then to clean up our structure, I'm going to draw it up here. And here on the central atom for the iodine, we're dealing with sp3d hybridization because there are 5 bonding domains, 2 lone pairs, 3 bonded atoms. For SF2 looks a lot like, well, H2O. The sulfur here can bond to the fluorines without hybridizing. Or without expanding its octet. Obviously, hybridization occurs. So again, expanded octet is one of those things, like each time we have a discussion, we're adding a layer, but we're also adding this complexity where we have to start ranking like what's a good idea in terms of stability. Formal charges obviously are big end of the line, check that. But expanded octets are one of those like as needed things instead of a do it all the time thing. So SF2, relatively, like that's perfectly fine stable compound. SF6 does work. Here this would be an sp3 hybridized sulfur. We've got, again, 4 bonding domains. And then for SF4 we can do the same process. I'm going to go ahead and start making my bonds. We've got one here, we've got one here, and then I think we have to split up one more pair to make everything fit. So then to draw things out, it would look like this. And then this would be 1, 2, 3, 4, 5. This would be sp3d hybridization. So IF3 and SF4 have the same electron hybridization, the same orbital hybridization as each other. They have a different structure about them because one has 4 bonded atoms in one lone pair versus 3 and 2. Thanks for watching.